Let's say you're standing here in New York City and you want to drive all the way across the country. Your destination is San Francisco. Finding the absolute shortest path between these two coasts requires navigating a massive, continent-wide labyrinth of roads. This map of North America shows over 64 million road intersections. Checking every possible sequence generates 10 to the 220th power routes. Even checking a billion routes per second, it would take over 10 to the 200th power years to finish. Yet, when you type that exact trip into your phone, it spits out the perfect route in about 4 seconds. Those servers aren't doing the impossible math faster. They are bypassing the brute force completely, using a mathematical trick. The roots of that trick trace back to a shopping trip in Amsterdam in 1956. A programmer named Dijkstra was working on software for an early mainframe computer called Armac. The general public thought computers were practically useless, so Dijkstra needed a highly relatable math puzzle, like finding the shortest path between two Dutch cities, to prove Armac's power. The simplest digital navigation method at the time was known as a breadth-first search. Starting from one city, the search branches out uniformly, checking neighbors 1 step away, then 2 steps away, expanding until hitting the target. But this assumes every connecting road is the exact same length, treating a straight highway and a winding road identically. To navigate the real world, a computer needs to actively evaluate and compare uneven distances on the fly. That requirement led Dijkstra to invent an entirely new approach to pathfinding. Dijkstra's idea was to keep a running tally of the shortest distance from the starting point to every intersection along the way. He called this running tally the cost. This animation illustrates his method. At every step, the algorithm asks if the current path to a new intersection has the lowest cost seen so far. The numbers hovering over the nodes represent that cost. If the algorithm finds a faster route to an intersection it already checked, it immediately drops the old cost and updates it to the new lower number. It always explores the lowest cost paths first. By meticulously exploring paths in order from lowest to highest cost, it naturally rules out longer detours. Once it finally reaches the destination, it guarantees you have found the absolute shortest possible path. But when you apply this to an entire continent, a glaring inefficiency emerges. Because Dijkstra's algorithm searches purely by lowest cost, it expands blindly in every direction at once. To find a path from New York to San Francisco, the search frontier spreads out in a massive 360-degree circle, exploring millions of roads in Florida and Maine before it ever reaches California. While the logic is perfect for navigating a small town, that blind circular expansion causes a massive data bottleneck. Running this across North America takes about 7 seconds per query. Engineers eventually figured out ways to guide the search. This graphic shows a modified version called A*. By calculating the straight-line distance to the destination, the algorithm penalizes any movement that heads in the wrong direction. The map effectively tilts, creating steep hills for wrong turns and forcing the search to flow naturally downhill toward the goal. Another clever patch is a bidirectional search. Instead of just starting at the source, the algorithm runs simultaneously from both the start and the destination, expanding until the two frontiers meet in the middle. Yet, even with these directional fixes, the computer still lacks basic human intuition. When you plan a road trip, you know you'll use a few local roads, hop onto a major interstate, and then take local streets again at the end. The algorithm doesn't instinctively understand road hierarchy. If a twisty neighborhood cul-de-sac and an interstate highway have the exact same mathematical weight, the computer will waste precious processing power checking every single driveway along the route. Until the navigation system can comprehend which roads are actually important, it will always suffer from computational waste. The solution to that waste is a technique called preprocessing. Instead of forcing your phone to calculate everything from scratch, server farms do the heaviest mathematical lifting offline, years in advance. They analyze the entire network to find massive geographic bottlenecks. If you want to drive east to west, you eventually have to cross a major river. All cross-country traffic funnels through a select few bridges. This visualization demonstrates how the system ranks all 64 million intersections by importance. It pulls the massive 2D web of roads up into a 3D pyramid. The major bottleneck bridges and interstate highways sit right at the peak. while the millions of local side streets are left down at the wide bottom. This structure is called a contraction hierarchy. Once the pyramid is built, the servers pre-calculate and hard-code shortcuts directly between these high-ranking nodes, ensuring the algorithm will never overlook a faster path. By pre-building these continental shortcuts, a live query on your smartphone no longer calculates the whole trip. It only has to search up the local hierarchy to find the quickest path to the nearest major on-ramp, and the shortcuts handle the rest. This comparison chart shows the sheer scale of the improvement. On the left, the old Dijkstra method expands into a massive circle, checking millions of unnecessary roads. On the right, using the pre-processed hierarchy, the search is a tiny hyper-focused cluster of roughly 1,200 nodes that instantly jump from New York to San Francisco via the top-tier shortcuts. That efficiency drops the query time from a sluggish 7 seconds down to under a single millisecond. We didn't solve that impossible 10 to the 200-year math problem by building a faster computer. We solved it by mathematically eliminating the need to check all those routes in the first place. There is a wonderful irony buried underneath this hyper-advanced continent-spanning digital network. The core engine executing the search through these pre-processed shortcuts is still the exact same original algorithm Edgar Dijkstra invented. Dijkstra firmly believed that simplicity was the ultimate prerequisite for reliability. He designed his algorithm in his head, without a pen or paper, which forced him to avoid any unnecessary complexity. Decades of engineering have stacked massive hierarchies and clever heuristics on top of it. But every time your phone finds you a route, your journey is quietly steered by an elegant, simple solution conceived on a Dutch cafe terrace in 1956.